So now we're going to try to find a cubic polynomial for a compressibility factor. And the reason we want to do this is that a lot of times when we're solving a problem, we're going to have our pressure and we'll have a temperature, and we want to solve for a volume. So we know that our compressibility factor is equal to PV over RT. And when we have our temperature, we obviously have R, which is just a constant, and we have our pressure. It's pretty easy to solve for V. Now the issue with this is that we have to find a way to solve for Z first, and then it's pretty easy to solve for V. So we have our old van der Waals equation, and that's just going to be equal to R times T over V minus B minus A over V minus B squared. So from here, we can come up with something called the generic cubic equation of state, and you'll see why it's called a cubic equation of state, but the fact that it's generic means that there's a bunch of different methods for calculating the pressure, and depending on which method you choose, you can just change the values of some of the constants we're going to be using. So we have P equals RT, but this time we're going to add in a, well, not in this term, that term remains the same, but we're going to add in two variables, or two constants I should say, one of which is going to be epsilon, and the other, oh, my drawing tablet's falling apart here. There we go. And then the other is going to be sigma. So from here, as you can see, we have our pressure, we have our RT over V. So we want to find a way that we can get this side of the equation, the pressure, to be equal to our term for compressibility. So let me get rid of all those circles. We have PV over RT is what we want. So to get to there, we multiplied by V and divided by RT. So since we divided by RT, we'll have a 1 up here, and then since we're multiplying by V, that just becomes a V, and then will be V minus B. Oh, that should have just been a minus, and then A. And then again, we're multiplying by V, and we're dividing by RT, so we'll have RT V plus epsilon of B, and then V plus sigma of B. So let's clean that up a little bit. And then from here, we can just re-express it a little bit. We'll have Z is going to be equal to 1, and in case you didn't see how I got that, we're just factoring this out. And then we'll have 1 minus B over V, and then minus A over V RT 1 plus epsilon B over V 1 plus sigma. I'll try that one more time. Sigma B over V. So from here we can do a little more finicking. We'll substitute some things, and we're going to come up with a cubic polynomial in just a few steps. So now I've written down a few equations for a few terms that we're going to be using, beta and Q, and you'll see why in just a second. So if we take a look at our Z equals PV over RT, if we want to solve for V, it's pretty easy. It's just going to be Z RT divided by P equals V. So now we're going to actually plug this in for our volume into our equation. So let me go ahead and give me a little more space. I'll get rid of this old mark here. So now we have Z equals, and now I'm plugging in our equation for V, ZRT over P. And when I plug that in, I have 1 minus B over V, which is going to be ZRT over P. Since it's in the denominator, we can just go ahead and flip it. So we'll have, oh, sorry, that should be P pressure over ZRT. And we can do the same thing for the next term. Well, actually, let's take a look at this. We have this right here. We have A over VRT. Now, if we want to plug this in for, or plug this in for v, all we have to do is do the same thing as before, just over here, and we'll end up with z r squared t squared over p, and then flip it, we'll have, I think that's a bit more mathematically sound, we'll have a p over z r squared t squared. And maybe you can see where we're going with this, but now we're getting closer and closer to being able to substitute for our beta and our q. So let's go ahead and write that down over here. This time we'll say we have our A times our pressure over Z R squared T squared. And we're going to do the same thing over here as we did over here. We'll have 1 plus epsilon BP over ZRT, and then we'll have the same thing with sigma. We'll have 1 plus sigma of BP over Z, and it's getting a bit too sloppy. I wish this thing would let you just draw a line, you know. We have sigma BP over ZRT. So now we can start finding ways to plug in our beta and our q to simplify it a little bit more. Let's look a bit closer at our numerator here. So again, gonna give myself some more space once I find my cursor. And so we have AP over Z R squared T squared. So if we go look up at our, again, I lost my cursor. It's a real pain to navigate this. Should probably use my pen more. So if we look at our beta, wherever we wrote that down at, oh, there it is, duh. We have beta equals BP over RT. So when we look at this, we see that we have our P, we have our R, and we have our T. We have to find a way to express this in terms of beta. So you'll notice that if we have P over RT, this is the same as beta over B, because you see we have this B, they would cancel out. Same thing. That's a terrible B. So if we were to do this for our equation, we'll end up with A times beta over B times R times T times Z. And then you'll notice that our Q is A over BRT. So now we have this is our Q. So again, we can rewrite this. Ditto beta times Q over Z is the same thing. So now we can plug that in as well. And then we also have this term here. We're going to have BP over RT, where we'll have this term, and we'll also have this term that we can factor in beta for. So let's go ahead and do that. And I'll give myself a bit more room. We don't need to rewrite beta. Z is going to be equal to 1 over 1 minus, one more look at, so we'll have beta over Z. And let me double check that. Always worried about messing up our beta here. BP over RT. That looks good. Minus, and then of course we can rewrite this as beta times Q over Z. And that is going to be over 1 plus epsilon beta over z, and then 1 plus sigma beta over z. So now is where the fun really starts. So we can take a look at our equation up here, and if we divide everything by z, we'll obviously have 1, and that's going to be equal to 1 over z times our same term as up there. And then we could do this in 2 steps. I'm going to go ahead and do it in one just to save us a little bit of time. We'll have z minus beta. It is surprisingly hard to write beta for how close it is to b anyways. And then we can re-express this as beta times q over z. And then we'll have the same term that we had before. I'm going to try some little magic here. There we go. It pays to be lazy sometimes. There we go. And then if we put down another z down here, we can multiply everything through again. And now I have to erase the stuff that I was so proud of copying. Oh, I didn't copy. It's fine. 1 plus epsilon of beta over z. 1 plus sigma beta over z. Okay, we'll do this the hard way then. So, and then we'll have a z on the other end. 1 plus epsilon and times beta over z. And then we'll also have 1 plus sigma times beta over z. And again, we can multiply through. So we'll multiply this one through here. And that's why I wrote it kind of in a weird way, just so it's a little easier to visualize how these are going to multiply through. So over here, we're going to have z plus epsilon times beta. And then over here, we'll have the same thing, but with sigma. So from here, you can see when we multiply these through, we're going to get some form of polynomial. So we're starting to get to the point that we can start solving and finding a cubic polynomial in terms of z. So now we're going to multiply everything by the common denominator. So on the left-hand side, I'm actually going to leave this kind of split apart a bit, and then we'll go through it term by term. So we're going to have a z minus beta multiplied by our z plus epsilon beta, and then our z plus sigma beta, and then on the right hand side we're going to do the same thing. Over here we're going to have a z plus epsilon beta, a z plus sigma beta, and then we're going to have a negative q times beta multiplied by our z minus b. Okay, so the form that we're shooting for here is going to be x cubed minus ax squared plus bx plus c. And what we're looking for here are these coefficients, because we can use these coefficients in something called the Cardano formula, or Cardano's formula, I should say, and then we'll use the roots of this cubic polynomial. We'll plug those into our equation for volume, which will give us the specific volumes, and then we can use those specific volumes to help plot our Maxwell construction and eventually a two-phase envelope on top of our isotherms. So let's take a look at this. We'll start off with our z cubed. Then we'll have a column for our z squared. Then we'll have a column for our z's, and then we'll have a column for our coefficients, or our constants, I should say. All right, so let's go through this term by term. And actually, you know what? I'm going to split up this left side a little more. We'll move all of this down. We'll move our poor one and the line down with it. All right, and then let's take a look at our left side here. We're going to multiply these two terms together. So we'll have a z squared, our plus epsilon sigma, or epsilon plus sigma. Let me try that again. Epsilon plus sigma times beta, and then we'll have our epsilon sigma beta squared, and then all that will be multiplied by z minus b, and then we're going to keep the z minus beta, I should say, and we're going to keep the right side how it is. Okay, so let's go through this term by term. So here we're going to take this z and this z and multiply them together. That gives us our z cubed. Here we're going to take our z times our epsilon plus sigma times beta. That is going to give us one positive epsilon plus sigma times beta coefficient. And we'll do that for our third one here. Same thing. Or actually, sorry, that should have a z there. So this term is actually going to get moved over one. If it'd let me erase it or select it, either one works. All right, so let me double check this. We got our z cubed, check. We got our z squared, looks good. So now we're going to have our z. So we'll have epsilon sigma beta squared times z, and then we'll do the same thing with our negative beta. So with our z squared, we're going to have negative beta times z squared. Then we are going to have negative epsilon plus sigma beta squared times z. And then finally, we're going to have a negative epsilon sigma beta cubed. And then we're ready to move on to the right-hand side. So let's take a look at this. This term here is the exact same as this term here. So we can pretty much just take what's in here and flip the signs. Because, again, we're trying to set it up so it equals 0. We want to move everything to the left side, so we're just going to take the opposite signs of what these are. So we have a z squared, and that'll be negative, so that'll be negative 1. We have a negative epsilon plus sigma times beta, so that'll be a negative epsilon plus sigma times beta. And then finally, we'll have another negative epsilon sigma beta squared. And we're ready to do this term here. And we'll have a, let's see, this first one here is going to be negative q times beta. And then the second one is just going to be so since the sign on this first one is going to be negative, it's actually going to be a plus q times beta. And I'll just mark this one too. And I'll mark this one too. And I'll mark this one too. Better safe than sorry. And then we have a, looks like a positive because these negatives are going to cancel. So we'll have a negative, looks like a q times beta squared. So this is the form of our cubic polynomials. If you wanted to write this out, you just put these in for a, b, or let me just write it, a, b, and c. And then you could express it in the form that we talked about above. But now we can use this, and we can use Cardano's formula to solve for the roots of this, and then we'll be able to use those roots to plot some things and show a two-phase envelope superimposed on some SRK isotherms later.